Yeah, once again, welcome you all to this course, Measure and Integration. To begin with, I would like to share a few words on course content. A major part of this course will be about Lebesgue measure on R, or more generally on Rn, and Lebesgue integration. This Lebesgue measure and the concept of Lebesgue integration were introduced by French mathematician Henri Lebesgue, I think 1902 or so, beginning of 20th century anyway. So major part of this course, we will be concentrating on constructing Lebesgue measure and developing Lebesgue integration theory on R, or slightly more generally Rn. And then we shall see how powerful this Lebesgue integration theory is in comparison with the integration theory that you know. What is the integration theory? The first and foremost integration theory that you are familiar with? Can somebody?
Riemann
Riemann.
integration.
Riemann. We will see the power of Lebesgue integration in comparison with the first formal theory of integration, namely Riemann integration. How powerful this theory is. In the process of doing so, revealing the power of theory of Lebesgue integration, we shall develop the main theorems. The main theorems are about convergence of Lebesgue integral, namely monotone convergence theorem, dominated convergence theorem, Fatu's lemma, and so on. These are the powerful fundamental theorems which reveals why Lebesgue theory of integration is more powerful than Riemann integration. And we shall also discuss about space of Lebesgue integrable function. If you collect functions that are integrable in Lebesgue sense and define a suitable metric on it, you will get a standard space, so-called capital LP space. L stands for Lebesgue. P is the exponent of the integral. So what we are looking for is those functions roughly for which mod f power p is integrable. Those functions f for which modulus of the function rise to power p is integrable. Integrable in the sense of Lebesgue. Okay, and those will constitute one of the main space that analysts use to work with in any branch of analysis, like partial differential equations, functional analysis. Those things are the courses that you are going to study in the coming semesters. So this course is going to be prerequisite for many other analysis course, and also it is a fundamental tool for analysts in general, measure and integration. Okay. And in the last part of the course, as I told you, the major part of the course will be handling how to construct Lebesgue measure, a particular type of measure due to Lebesgue, and in connection with it, a particular type of integration called Lebesgue integration, mainly on Euclidean spaces. However, the last part of the course, I would like to introduce abstract measure spaces and abstract integration theory. More general than concrete Lebesgue integration and Lebesgue measures. Abstract measures and abstract integration theory. In fact, one does not have to do any extra effort to develop abstract measure and integration based on that abstract measure. Whatever one does on Lebesgue measure constructed on R and subsequent Lebesgue integration can be copied to develop more general setting, the so-called abstract measure and integration over that. One can just copy the essential material on Lebesgue measure. However, personally, I feel that concrete examples should precede the abstract thinking. So you should have experience of working with some particular examples before going to abstract concepts and abstract theory. Because of that principle, I would concentrate first on particular measure called Lebesgue measure and particular type of integration called Lebesgue integration, which of course is connected with the Lebesgue measure, and subsequently deal with abstract measure and abstract integration. Okay. Of course, the reverse is also possible. If you see many standard books, they start with abstract measure and abstract integration and then talk about particular measure called Lebesgue measure and Lebesgue integration. So there are both ways possible, from concrete example to abstract, or first study the most general abstract things and then come to several particular concrete cases. But as I told you, I personally prefer that, or I personally believe that we should have at least some concrete examples, how it works, intuitively how these things are being developed in order to understand what is going on in a general theory or in the abstract setting. So I will follow this philosophy. First introduce the very special case of measure, namely Lebesgue measure, and connected with it, a very special type of integration, Lebesgue integration. Talk how Lebesgue integration is powerful compared with Riemann integration. Develop the theory for Lebesgue integration, and then quickly talk about abstract measures and abstract integration. Once you are okay with the Lebesgue measure, the abstract measure is not going to be a big deal. It is going to be a cakewalk. So far, so good. Of course, there are several technical words involved, Lebesgue measure and Lebesgue integration and so on. The purpose is not to understand those things now. My intention was to give what this course is going to be about. Basically, this course will deal Lebesgue measure and a connected concept, Lebesgue integration. Okay. And as I told, this is going to be one of the prerequisite for many analysis course and related courses. Okay. So far, so good. Let me tell you that I would expect response from you, and I would also suggest at least quite frequently, if you can switch on the videos, it will be beneficial. But seeing your face, I can understand whether things are going fine or not. Okay, so I would request your videos to be on, if not for the whole lectures, at least quite frequently. So far so good.
Yes, sir.
Yes, sir.
You got some flavor of what this course is going to be about?
Yes, sir.
Okay.
Yes, sir.
So if that is the case, now let me mention a few references that will be useful for this course. As I hinted at, this course is very classical and a standard course. In fact, Lebesgue introduced this concept in early 20th century, 1902 or so on. And after that, this has been a source for development of many other analysis branch, like functional analysis, partial differential equations, and so on. Because of the same reason, there are umpty number of books handling this subject, measure and integration. However, as I told you, if you go through different sources, there are two approaches. From concrete, go to abstract, or first introduce abstract setting and subsequent chapters will discuss concrete cases like Lebesgue measure and so on. Okay. Since my interest is to develop Lebesgue first and then abstract, I would suggest the following references, which also follow the same concept. First introduce Lebesgue measure and then talk more about Lebesgue measure in detail, compare it with Riemann integration theory and so on, and finally introduce abstract measures and abstract integration. That approach you can see in the following references, which I will use mainly for this course. All are very standard references. First book is by D. Barra. The author's name is G. D. Barra, and the title of the book is Measure Theory and Integration. Measure Theory and Integration. Fortunately, this book is downloadable, I hope. Freely downloadable. It is a very concise book, written in a very concise manner. Very small book, but the treatment is very good. Another standard book which we shall refer to for the first part, Lebesgue integration, Lebesgue measure, and so on, is by Royden, another classic book, Real Analysis. The title of the book is Real Analysis. And for the last part, namely abstract measures and abstract integration, I would mainly use the third reference. You might have heard about this author, Rudin. Did you use this book for real analysis by any chance?
Yes, sir.
Yes, sir.
Yes, sir.
But then I am not sure which book of Rudin you have used. There are mainly three books. One is basic analysis, mathematical analysis or something. I don't remember the title. That is popularly known as Baby Rudin. And what I am referring to is the second book by Rudin, Real and Complex Analysis. Real and Complex Analysis. Most probably in the real analysis course, you might have used the first book on real analysis.
Yes, sir.
Yeah, this is the second book by Rudin, Real and Complex Analysis. Okay. So these are the three books I would suggest. And my lectures will be mainly based on or the blend of these three books. But let me also tell you that no book whatsoever you pick up is going to be a substitute for the lecture. It can supplement the lecture, but it cannot substitute the lectures. I'm not saying my lectures are so great that no book can substitute it. But what I mean is the following. Of course, as I told you, this course is one of the core course which becomes background for many other analysis course. So we too had many difficulty to learn this course as a student, later as a research scholar. When we have to apply these tools in our own research area, we had several difficulty. And also as a teacher, when I taught this course for students, I experienced certain difficulty from their level and so on. So all these experiences as a student, as a research scholar and teacher will help me to tune my lectures. So, and moreover, the emphasis of lectures would be to the conceptual understanding rather than the definition, theorem, proof style. But most of the books that I have given here follows that philosophy. Give the definition, write a theorem, prove it rigorously. But what is the motivation? Why do you want to define certain things like this? What is going on in that theorem, in the proof, and so on? That an intuitive flavor I will try to give during the lectures. And those may not be available in books. That's why I told no book whatsoever you select from Google or whatever is going to be a substitute for the lectures. Not for my lectures, for any lecture. Okay? Because we are tuning the lectures with our own experience as a student, as a teacher, as a research scholar, how I should blend all the sources, different resources available so that the students can easily pick this idea. We are planning, we have more time than you. You have to do 5 courses in this semester, whereas I have to work only with maybe 1 or 2 courses and my research topics. So we have enough time to compare, contrast various resources, and consolidate. And please have a trust that the instructor will give you the best out of all these books. Okay, are you with me?
Yes, sir. Thank you.
So the moral of the story
Yes, sir.
is, moral of the story is, There is humpty number of books available on measure and integration, and maybe humpty number of video lectures also nowadays in YouTube. But don't skip the lectures just because, okay, the things are available somewhere else. Okay. No source is going to be a substitute for the lectures given by me. Not because I am a great teacher. Let me repeat. Again, let me repeat that my emphasis on the lectures would be conceptual understanding, how intuitively things work, how one has been motivated to define certain things, starting from what is available, how it has been developed, and so on. So let us try to understand things rigorously rather than mugging up. Okay, this is the statement of the theorem. This is how the proof works, and so on. Even while reading the proof from book, I would suggest you not to read line by line. The proofs should not be read line by line. First of all, don't read proof from the book. You try to prove it your own. Possibly you may not succeed. Then take a book and just see what's the main idea of the proof. What is the crux of the proof? Take only that from the book. Try to develop the proof your own. You may not succeed. Again, look back at the textbook proof. See what are the details given. Therefore, the proof should be read from a book, not at a stretch, in many phases. Okay. First of all, try to do it your own. If you don't succeed, try to pick the main idea of the proof and write your proof your own in a very detailed manner. Sometime you may skip some steps and so on. Then again, look back the book and so on. So it should be like, no, it should be done in several phases. But usually, including me, what I have done is take a book and read all the proof, all the details from the proof, close the book and try to recap those or try to recall that proof. In that way, you may be able to give a proof at that time. After a few days, you will forget. And it will look like the proof is entirely new to you. That time you might have, okay, I understood the proof. But that's not the way to understand. If you want to really understand a proof, you should understand what is the crux of the matter, how the proof is being developed, what's the main idea involved in the proof. Also try to see what are the hypotheses in the theorem, where exactly in the proof those hypotheses are being used. This step, this hypothesis is used. In that way, you should always highlight where a particular hypothesis of the theorem is used in the proof. Okay. Not only that, after the proof, you should ask if this hypothesis is not there, what will happen? That means you should supply with counterexamples. If this particular hypothesis is not there, whether the proof works. If that particular proof does not work, that doesn't mean that no other proof will work without that hypothesis. Okay. So what I mean is the following. There is a particular hypothesis in the theorem. You took a proof and you could locate that that particular hypothesis is used in this particular place of the proof. You could locate, suppose. I hope you are with me. A particular hypothesis is used in a particular place of the proof. You could locate. Okay. That doesn't mean that without that hypothesis, the theorem is false. Do you agree?
No.
Why?
How?
Because there may be a different proof by a different person who doesn't use that particular step or a particular hypothesis. So you could see that a particular hypothesis is used, say, in nth step. That doesn't mean that without that hypothesis, the proof will not work. Maybe there is another proof which works without that particular step. Are you with me? So if you really want to understand importance of the hypothesis, what you try to do is try to get examples where that particular hypothesis does not hold, and consequently the result dictated by the theorem also does not hold. So this is an example where the hypothesis is not true and consequently the conclusion of the theorem is also not true. Suppose you could come up with this example that will tell us that, okay, without this hypothesis, the theorem is not true in general, because you could produce an example where without that hypothesis, the things are not working. Are you with me? Of
Yes,
course.
sir.
And since you
Yes.
have completed several courses in mathematics, this is not new to you, but I thought it is my responsibility to share. So never ever just read the proofs as such from the book. Try to understand the crux of the matter and then try to write the details your own. Okay, one thing. Secondly, always ask where hypotheses are used in the proof. This is where this hypothesis is important, that you should try to understand. But that alone will not give you the fact that without a particular hypothesis, these results are not true. If you want to ensure that, you should supplement your proof with examples. Try to construct examples where the hypothesis of the theorem is not true and consequently the conclusion ensured by the theorem is also not true. So you can guarantee that without this hypothesis, in general, the results may not be true. For example, in this particular example, it doesn't work. Okay, so supplement your proof with counter examples. In the sense, take examples where hypothesis is not true and consequently conclusion is also not true. Similarly, certain times you may be able to see that hypothesis is not true, but the conclusion is true. Then you can guarantee that conditions are not necessary. Those conditions imposed in the theorem are not necessary. Okay, this was not planned, but somehow it crept into so you should try to understand the proofs in such a manner and try to explain the proof to a layman without using this jung epsilon delta corresponding to every epsilon there exists a delta. This you might have been seen from +2 and you are using till now. That's okay. For a rigorous proof, you need epsilon delta, all this rubbish language that mathematicians use. But at the same time, try to explain it in common man's language. Okay? Try to explain this to somebody who doesn't have that background. If every time we may not succeed with it, if we have succeeded with it, that means we understood the thing clearly. If you are able to tell only in terms of epsilon delta, all this magical language, that means you have not understood the things clearly. You, I mean, including me. Okay. Sometime if I say, okay, this is how the proof works, that means I did not understand the proof really. That's the meaning actually. Okay. So we may always use these fancy languages, epsilon, delta, that, this, and so on. Mathematicians are always crazy. But I would suggest, please try to understand the proof and try to explain the proof to a layman. What is going on? Okay. Okay, with that, so these are the references. Now, prerequisite for this course, as I already told, may be calculus and analysis, which anyway you have done as a core course in the previous semester. So there is no issue with the prerequisite. So if you are okay with real analysis, then this course background is there. Okay. And what more I should say? Attendance policy, if you ask, I don't have any strict attendance policy, I will say. Okay. But as I already told you, no textbook or no resource is going to be substitute for the lecture. So it is your responsibility for the material covered in the lectures. Okay. So if you feel that all these materials I already know or I already can get from somewhere, feel free to skip the class. I don't mind. Okay. But at the same time, for those who are attending the class, you should be on time. Don't, especially in this online mode, don't just enter at 8:30 or 9 o'clock and then no, don't do that. I know this is winter, 8 o'clock is slightly difficult. All these things I know, but try to be on time if you really want to attend. Otherwise, you feel free to skip. I don't mind it. Okay. Yeah. So that's it about my attendance policy. So I don't take attendance even in physical classes. Okay. But that you should not be a freedom for you to skip the classes. If you feel you will be benefited out of this, please feel free to attend the classes. Okay. So that's about attendance policy. What more I should say about grading? Do you want to know about grading? Yes. Okay. Of course, you all will be concentrating mainly on this, I know, but don't do that. Okay. Don't study any subject just for grade and marks. Try to understand the subject. But anyway, I know the grade is also important. So, and also it is a part of any course. So the grading or evaluation will be based on minor, of course, as per the institute rule. I think since this is an online, I think it is only one minor is there. So if there is only one minor, I will stick to it. If there are two minors, then so whatever institute policy is, and one major, of course, as per institute. In addition, I would try to conduct at least one quiz. Of course, I want more quizzes, but I don't know whether time will permit for that. And roughly, as of now, I am planning like this: 30% of the evaluation from minor, 50% of the total evaluation from major, and 20% I will reserve for quiz or quizzes. That depends upon the time availability. Roughly, if at all there is some modification, I will let you know. Okay. But let me just confirm from you, as per institute calendar, it is one minor or two minors?
One minor, sir.
One minor.
Okay. So this is all about the grading. Now, as a 4-credit course, as you all know, tutorial is going to be a must component. Okay. And I want 1 hour per week for the tutorial. And I would like to handle tutorial my own. I am not going to take help from any tutorial assistant. Whether it is good for you or bad for you, I don't know. But why I don't wanted to take assistance from tutorial, research scholars, is the following. First of all, I would like to know how good you are with the concepts applied in the lectures. If somebody else is doing the tutorial, I may not be able to know that. Secondly, these lectures and tutorial, as you know, one complements the other. Therefore, if myself is handling tutorial, I may manage according to, for instance, it's not like every week I will conduct exactly one tutorial. Not like that. I will be conducting tutorial only when I feel that you are ready with the enough material on the lectures. I repeat, though I am going to reserve one tutorial per week, it will not be conducted in a very regular manner in the sense, it may not happen exactly on the tutorial hour or something. When I feel that you are ready with enough concepts, materials on the lecture class, I will conduct a tutorial. So some lecture class may be converted into tutorial, and the tutorial that I am going to assign per week may be used for lecture class as well. So it is vice versa. Are you with me?
Okay, sir.
Yes, sir.
And also tutorial sheets will not be uploaded very regularly. I know, okay, this is the stage where you are ready with the materials, and this is the stage I have to give more examples and problems. Once I feel that, I will post a tutorial sheet. And then accordingly, I will conduct the tutorial classes. Of course, before conducting tutorial classes, I will be posting the tutorial, but tutorial classes will not be conducted regularly per week. Initially, for this week, definitely there is no tutorial. From next week onwards, we will start tutorial in principle, but in practice, those tutorial classes also will be used for lectures, maybe. And later when I feel, okay, this is enough, now we can be ready. Some lecture hours may be converted into tutorial. So in that way, if I want to do that, I have to handle the tutorial myself. So as I told you, whether it is good or bad for you, I don't know, but I will be going to handle the tutorial myself. Okay. Now, as I told you, we have to fix 1 hour slot for a tutorial per week. I don't think institute has given a particular slot for this. Am I right?
There is 1 to 2 each day.
1 to 2.
When, which day?
Every day.
Oh, every day 1 to 2 for tutorials. I mean, subjects, any courses that you are doing.
Yes,
But
sir.
which course that we have to decide according to the coordinator and student. That's what you mean?
Yes, sir. Yes, sir.
Okay. But I don't think 1 to 2 is going to be an appropriate time. Let us see if it is not suitable, that I am going to propose some time. If it is not suitable, definitely we will stick to 1 to 2. Otherwise, I would like to propose the following, because I have gone through your courses and the corresponding slots, and I felt that you don't have classes from 11 to 12 or 12 to 1 on Wednesday or Friday. So this is my proposal. You can discuss among yourself and let me know. So Wednesday or Friday, 1 hour slot between 11 and 1. 11 a.m. to 1 p.m. 1 hour slot. Either 11 to 12 or 12 to 1. Is that okay? Yes. Anchal, Aarti, Abhishek, Meena, Aman Chowdhury, some of you should respond. So this is my proposal. I am not fixing it for the time being. I think you may have WhatsApp group of your own or whatever it is. Please discuss among yourself and let me know by this weekend. In principle, from next week, we should be ready with a tutorial slot. Is that okay?
Yes, sir.
Yes, sir.
I observe that most of your courses are in the afternoon slot. Except,
Yes, sir.
except this course. Sorry to bother you, that too in the winter 8 o'clock. Yeah, I know now how much you will be cursing me and this subject. Okay. So whereas the other subject, you can come in a relaxed manner, especially if it is physical classes. Okay. So I don't mind it. I felt that you will be more fresh at the early morning. Okay. And 1.5 hour slot is relatively better. If the theorem proof style and the proofs are very lengthy, splitting into 2 different classes is not ideal. So 1.5 hours, I may be able to finish some proofs rather than splitting into 2 lectures. By the time the next lecture comes, you may forget what was happening in the previous. So that I don't want to happen. That is one reason I went for 1.5 hour slot. Okay. Anyway, so please discuss among yourself and let me know. This is my proposal. 1 hour Wednesday or Friday. Okay. Is it clear?
Yes, sir.
Yes, sir.
So
Yes,
this is
sir.
about,
Yes, sir.
So I think all the basic ingredients required for the course I have given. So I talked about course content. Let us have a quick recap. The course content is mainly on Lebesgue measure and Lebesgue integration theory on the Euclidean spaces, and then why such a theory is needed. Why not just Riemann integration is sufficient? What are the deficiency of the Riemann? How this Lebesgue is powerful compared to Riemann, and so on. And final part of the course will be more abstract setting. And once you have learned this abstract, the Lebesgue measure and Lebesgue integration is going to be just one particular example. Something like vectors in plane or vectors in space is only one particular example of vector space. But vector space concept can deal with not only vectors in plane, it can also deal with, for instance, polynomials. It can also deal with, for instance, matrices. Okay, these matrices, polynomials, vectors in space, etc. Apparently, they are all different. But there are something common for all these things. That commonality you are studying through the concept of vector space. Okay, so what is the power of abstraction? The power of abstraction is that a common theory can deal different things. That's why you need abstraction, right? Yes or no? Have you ever thought why mathematics is behind abstraction? Have you ever thought, and do you have an answer for it? Yes, please. Whenever I ask questions, it is not to judge your knowledge. It is just a medium to interact with you. Okay.
No, sir. No, sir. No idea.
Yeah. So please don't think that I am judging your knowledge with the help of my questions. I just want you to give a chance to interact. That's it. And feel free to express your views. So have you ever thought why this abstraction? What is abstraction and why the abstraction? Why mathematics is behind abstraction? Have you ever thought?
No, sir.
You might have studied group, rings, vector space, many things, metric space. No? Why do you want to study such abstract concepts? No? Nobody want to respond?
Sir, think, but how to interlink each other? Don't know.
Yes, you are partially right. Okay. See, this abstraction is not something new that you are doing right now when you do higher level courses. Even from the very beginning of mathematics, you are doing only abstraction. Now, abstraction means what? Abstraction means, in layman's language, the following. Take only the necessary things what we want and leave the details. You take the essence and leave the unwanted details. That is what abstraction is. Now, of course, the question is, what is the essence that we have to take and what are the unwanted details that we can omit? That definitely depends upon the problem at hand. I cannot give a unanimous answer for it. But a vague understanding of abstraction should be, abstraction means studying or viewing only the core or the essence and just forget about all other unwanted details. For instance, in school classes, something like this you always come across. You are being supplied with, let us say, 5 apples by your mom and 8 apples by your father. How many apples you have total? Such questions you have come across in early days. Okay, 3 apples, and let us say 3 apples and 5 apples. How many apples you have in total? So what do you do? Do you really worry about whether it is apple or as far as mathematics is concerned, or you will just represent that 3 apples by the number 3 and 5 apples by number 5, and you will add 3 plus 5 and you will get 8? Yes or no?
Yes, sir.
Yes,
So
sir.
the
Yes, sir.
essence of that particular problem does not lies on whether it is apples or orange or something. It really depends upon only the abstraction. And what is the abstraction there? The three things, the three apples you represented by the number 3, which is of course an abstraction. Number 3 doesn't have any meaning as such. 3 apple has a meaning, 3 orange has a meaning, 3 boys has a meaning, but as such 3 doesn't have any meaning. 3 is only the abstraction of all these things. Okay, so like this, the abstraction is not something new that you are doing. You take the core of the problem and just leave the unwanted details. In this particular thing, what was the unwanted detail was apple. Apple was unwanted. Whether it is apple or orange or whatever it is, the answer is going to be the same. It doesn't matter. It is not relevant to the problem. Okay, it is only something additionally given to you. This is what you do in abstraction. Take out the essence, leave the unwanted details. And why? Why is it important? If you do that, for instance, in the same problem, I can pose differently. Suppose 3 men arrived at a party at 10 o'clock in the beginning of the party, and let us say, and 5 men arrived after some 10 minutes. How many are there now in that party? Somebody asked. Same answer is again 3 plus 5. I might have posed the problem differently, changing the apples by men and including the party and so on. But essentially the things are same. Like this, if you concentrate only the essence, different problems can be tackled with the same method. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
a
sir.
single theory may be useful to handle different situation. In the example I told, addition is the theory needed. Once you have addition, you can handle different situations like I have told, 3 oranges, 5 oranges or whatever it is. So like this, when you take out only the essence and leave the unwanted details, the benefit is that with a single theory, you may be able to handle different problems or different context. That is why abstraction is important. Now come back. I have told you vectors in plane, matrices, polynomials, all are looking different. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
But there are some things which are common in it. In essence, they are same in some sense. What is that common thing between these things that you pick up? You develop a theory for these common things, common features. And once you have done that, with one particular theory, you can handle these 3 different things. In our situation, vectors in plane you can handle, matrices you can handle, polynomials you can handle. So one single theory is enough for diverse areas. That is what abstraction is useful for. Once you have abstracted thing with a common theory, you may be able to handle diverse areas. Okay, this is where vector space coming into picture. Once you study vector space with the theory in vector space, you can handle matrices, you can handle polynomials, you can handle your usual physical vectors in plane or space. Hope you are with me.
Yes, sir.
Okay,
Yes,
so
sir.
Yes, sir.
let me just again repeat in layman's language. Abstraction means just viewing the essence of the problem without worrying about unwanted details. Okay, just look at the core of the problem. And why do you want to do that? If you do this, different problems which apparently different may have some commonality between them. You take that commonality, develop a theorem for that common feature so that with a single theorem or theory, you can handle diverse areas. Okay, and this is what abstraction is good for. Once you have abstracted things, No, with a single theory for that abstracted thing, you can handle different problems, for instance. Okay, so this is where for instance, in algebra, what we do, you study about group and how was it motivated. You consider, for example, integers with addition. They have certain properties. Another one, say matrices with addition. They also have certain properties. And these common properties you study, and that is about commutativity, associativity, and so on. And those common property you bring and make it as axiom and talk about something in abstract. That is what a group is. And once you have a theory for group, that theory you can use not only for integers, you can use for matrices, you can use for something else, and so on. So with this common theory of group, you may be able to handle different situations. There is no need to have different tools for different situation. One single tool may be enough to handle different situation. This is why we are always interested in abstraction.
Yes, sir.
Does it make sense?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
A common theory for possibly diverse areas. That is the purpose of abstraction. But I don't want to do that first. I want to concentrate first on some concrete example of measure, that is Lebesgue measure. And that will give you more intuition how it works, why measure and integrations are connected, and so on. So after doing that, I will slowly move to abstract things. But once abstract things are settled, the Lebesgue measure that you have studied will be only a particular example of abstract measure. And there may be many other types of measure also, not only Lebesgue measure. Okay. And once I have done with abstract measure, all these things that you have studied in Lebesgue measure is going to be a particular case. And moreover, whatever theory I developed for abstract measure will be applicable not only for Lebesgue measure, but also for different other kinds of measures. Okay, so abstraction is always good in the sense that with the one single theory, you may be able to handle different situations. Okay, again, this was also not planned. I was talking something about how to read proof, how to understand proof. I was talking about why abstraction, and abstraction is not something new. You have faced abstraction even from very elementary school classes. You did not know that you were abstracting, but you were actually abstracting. For instance, like problems 3 apples, 5 apples, and so on. There also you were abstracting only. Unwanted details like apple you left. You concentrated only on the numbers 3 and 5. You understood that what is important there is number 3, number 5, and addition. Nothing more than that. Okay. Similarly, look at different problem and understand what is really important to them. Take out that common important factors and make a theory for that common important factor. And that is what abstraction really is. Okay. So again, this will help you in any course, in any, whenever you study some abstract course, think like this. Okay, abstraction is for this. It was also not planned, but doesn't matter. Now, with the remaining time, let me say something intuitively about what this course is and how we will be progressing. Okay. So before entering to the formal treatment of the subject measure and integration, in the rest of this lecture, I would like to give you an intuitive overview, a layman's understanding of what measure and integration is. Okay. So let us again look back at the title, measure and integration. So the first question that comes to your mind may be, what is measure? Okay, what is measure? Why do you want to have a big course or a theory for measure? And also the question is how it is connected with integration. So these may be the questions that comes to the mind after seeing the title of the course. What is measure? Measuring what? Why do you want a theory for measure? If you see measure theory, I might have written in some name of the book and so on. Why do you want a big theory for measuring? And how is it connected with integration? So these are some questions that comes to our mind after hearing measure and integration. So let us try to answer this in an intuitive manner. Okay. Are you with me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
So before, as I told you, before entering to the formal rigorous treatment, let us see an intuitive overview of the subject. Okay. I would write intuitive overview. First question, as I told you, first question, of course, is what is measure? And how is it connected with the process of integration? Let us even forget about integration and connection of measure with integration and try to answer what is measure. Obviously, it is going to be something connected with measuring, no doubt about it. It is something connected with measuring. Now, measuring what? Why do you want a big theory or a big course for measuring something? Okay. Measure, whatever I am writing is just layman's language, not a rigorous mathematics. Okay, that we will enter later. Obviously, something connected with measure. Measuring. Measuring what is a question. Okay. Now, before that, do you know some early measurements that you have done, maybe in geometry or in school classes? What are some earlier measurements that you are familiar with?
So measurement of length, angle.
Length, area, volume, all these
Yes.
things you are familiar with, right? So I will call this as earlier measurements. Okay. Some of the earlier measurements, in the when I was say earlier, I mean from the time of Euclidean geometry, are length, area, volume, etc. This is not exhaustive list. I am just writing some of them. For instance, when you are talking about an object in real line, we quickly associate it with length. When you are talking an object in plane, Cartesian plane, two-dimensional plane, we try to associate with area. And when you talk about object in three-dimensional space, we try to associate it with volume. So object in R, the early measurements that one think about is length. Okay. And this is in R, R2 and R3 respectively. Let us concentrate for the time being only R. In R. So as I told you, the earlier measurement in R is length. Okay. Earlier measurement, Euclidean measurement is length. Okay, but suppose I am giving you a subset A of R. Let us say non-empty. Can you always talk about its length? Can we talk about length for any given A subset of R? What do you feel? Can you think about length for any subset of R? I am asking you. What do you think?
No, sir.
No. Length is mainly
Yes, sir.
for what? Length is mainly for what? Do you measure length for what?
So for finite set.
Finite sets, okay. Okay. Suppose I give you a finite non-empty set. Can you always talk about its length?
No, sir.
No, sir.
See, whenever you have length,
Sir, for
mainly
connected.
we talk about
At
length
least 2
for
points.
intervals, right?
Yes, sir.
Length you
Yes,
can
sir.
define for intervals in R. Mainly, I'm not telling only for intervals. First and foremost thing that you can handle with length is intervals. And for an arbitrary set, I cannot talk about length. Arbitrary subset of R. Okay? Length works fine for intervals. For instance, suppose your A is open interval AB. A is equal to open interval AB, subset of R. It's an interval containing all real numbers between A and B. I am not including A and B. Then you know length of A. What is length of A?
B minus A.
B minus A. All of you know this length of A is B minus A. But given a general set, general subset of R, we may not be able to talk about length. We want to generalize the concept of length so that I can talk about length or something like length to any subset of R. Okay. Length works fine for interval, but length may not make sense for a general subset of R. Okay. What we want to do is we want to generalize the concept and we want to talk about length not only for intervals but also for any subset of R to begin with. Okay, we want to generalize the concept of length and we want that generalized concept of length is called measure, and we want to measure an arbitrary subset. I am using all kind of languages here because I told you that I don't wanted to give you a rigorous definition now. This is all an informal things, intuitive way. Okay, arbitrary subset A of R. What do you mean by generalize? Of course, I wanted to have measure for intervals. And also I want measure for subsets which are not intervals. Okay. Further, if you want to call measure as a generalization of length, when you call it something as generalization, When you go to the particular case which is already available, it should coincide. Therefore, when I attempt to define measure of a subset, and if I take that subset as interval itself, what I should get as measure? Is the question clear?
Length of interval.
Yeah, correct. My attempt is to extend the notion of length. Right now, length makes sense for intervals. I want to go beyond intervals and attach length to any arbitrary subset. But when I do that, and suppose I want a good generalization, if that subset that I am taking is interval, then my generalized concept should coincide with what already is available. And what already available with the intervals are length. So my measure should coincide with the length if the subset happens to be what?
An interval.
Intervals. That's clear. So that then only you can call the measure something as a generalization of length. Okay. And moreover, I want the measure to be attached with something more than intervals, not just for intervals. For intervals, I already have length. Okay. So these subsets that I am taking should be rich enough to include all the intervals. It should include interval and it should include something other than the intervals. To be ambitious, you can ask, I want to measure any arbitrary subset. That may not be possible sometime. Okay, you may, for instance, length is defined only for intervals. Like that, when you try to extend the concept of length, you may not expect that it will define for all subsets of R, but it will define for a particular collection of subsets of R, which includes intervals as a special case. So it should be rich, the collection should be rich enough to include all intervals. It may not be rich enough to include all subsets of R. Maybe we will face some issues while attempting to define measure for any subsets of R. Okay, so before telling that, let me also mention the following. Now, if you really look at what length does, is the following. It assigns a number with all intervals. So you have collection of intervals, that is the set under consideration. You take all intervals and put it inside basket. And to each of the elements in this basket, you have an output, that is length. So length may be thought of as a function. It's a function from word to word. Can you tell me?
Collection of interval to R.
Yeah, it's a collection of intervals to R. Good. We can say something more. What it does, it takes an interval of the form AB and associate with that interval a number. And what is that number?
Positive.
A real number.
It's a
Positive
real
real.
number, B minus A. In fact, it is a non-negative real number, right? So I
Yes,
can
sir.
say that length assigns a non-negative real number with a very open intervals, or any interval. Why should be open? Okay. Note that what length does. What length does is to assign a non-negative real number with any interval. So if you want to put some notation, I will write non-negative real number L of I, length of I, with any interval I. Given an interval I, the output is L of I. Okay, L of I is equal to L of I am taking open interval. Nothing wrong in working with closed interval. It is b minus a. So if you view length like this, by generalization, what we mean is we want to assign a non-negative real number with every subset of R, not just with the intervals. Okay, we want to assign. This is what we want to do. We want to assign a non-negative real number with any arbitrary subset A of R. But as I told you, we may not be able to assign non-negative number with any arbitrary subset. We may have to deal with only some special classes of subsets of R. Okay, to be ambitious, I would write. To begin with, I can be ambitious and I can say that I want to assign a non-negative number with all possible subsets of R. Okay, that means we want to define a function. We want to define a function. That function I am calling as mu. Mu from, can you tell me from where to where we want? If you take L as
Collection
a
of subset
function,
plus
P of
R.
R.
it is power set of R, right? 2 power R. Power set of R means collection of all subsets of R. 2, I want for every subset of R, I want to assign a real number, not actually real number, such that mu of A is greater than or equal to 0 for every A in 2R. 2 power R, I mean power set, the collection of all subsets of R. This is what I want to do. Okay. There is no big deal about it. If you just want to define a function from 2 power R to R, there is no big deal about it. You can always define any function, right? Defining a function from collection of subset of R to you assign numbers to all subsets. What is big deal about it? Okay. So there is nothing much about it. However, what I want to do is that I want this mu to be a generalization of the length. Keep this in mind. I want this mu to be generalization of the length. So what are the things that comes to your mind? First thing that you come to your mind should be if A coincides with interval, suppose the subset that I am taking is an interval, mu of A should be
L of I.
L of I. Mu of
Length
A.
of the interval.
Length. Then only you can call it as generalization. That is first and foremost thing. Secondly, our experiences with the length will give that this mu should have certain principle. Mu should satisfy certain general principles. Because I want something as a generalization of the length. Therefore, this mu should satisfy certain properties which is enjoyed by the length. Okay. Then we should see what are the properties enjoyed by length. And those property we want not only for length, but also for this generalized concept which we are trying to define, that is for mu. And this mu of A, I will call as measure of A. So by now, two things should be kept in mind. One is that once you are attempting to define a generalization of the length, if I pick A to be interval itself, the measure of that interval should coincide with the already known measure of interval, namely length. Secondly, the mu that you are trying to define should enjoy the properties of length. And what are the properties of length that you know? Okay, so before that, let me write. Our experience with length suggests that mu should satisfy. So just like that, you should not define. Mu should satisfy certain general principles or properties enjoyed by length. Then only you can call this mu as measure. Okay. Now, what are the general principle that we are aiming at? Okay, I don't tell all the things, but let me at least mention one thing. Suppose you say, for instance, okay, for instance, the length of a wire, let us say is let us say 5 centimeter. Length of this wire is 5 centimeter. What does it mean actually? What is the meaning of saying something is 5 centimeter? Yes.
So if we measure it with a standard,
Very good. You have a standard measurement, standard unit of measurement. Here in this case, let us say 1 centimeter. With the help of this, if you try to measure the wire that is given, 5 standard units of measurements are needed to cover this wire. Yes or no? That's the meaning.
Yes, sir.
Right? That's the meaning. Okay. So what we are doing here is we are essentially using the general principle. The whole is equal to sum of its parts, distinct parts. Okay. When you copy this standard unit 5 times and you paste here in the original wire, the entire wire will be covered. So what does it means is that one principle we aim at is that the measure of the whole should be is equal to sum of the measure of its parts. Yes or no?
Yes, sir.
Now,
Yes,
again, when I say parts, I mean, again, these are not very rigorously talking, very intuitive. When I say parts, I mean the distinct parts. And when I say parts, I wanted to talk about only finite number of parts. When you cut it into infinite number of pieces and then join together, things like convergence, etc., will be an issue. Infinite sum you cannot handle. So if you have this given length of wire, you cut it into 5 pieces of standard wires, and if you combine them, you will get the original. Okay, so the whole is equal to sum of the distinct parts. This is one guiding principle that we keep in mind while measuring. Measure of the whole is equal to measure of parts, distinct parts. And when I say sum of finite number, okay, finite number. So if you have, so let us translate it in the language of mu. You want to define a function mu. Now suppose your object is made of several parts. Let us say A1, A2, A3, A4 and so on. Okay, let us say up to A5. And now I want to measure, and suppose that A1, A2, A3, A4, A5 are distinct. They don't intersect. Okay, and suppose now I want measure of the union set, A1 union, A2 union, A3 union, A4 union, A5. And our experience with the length tells us that measure of A1 union, A2 union, A3 union, A4 union, A5 should coincide with what?
measure of some of A1 their plus
Sum of the
individual.
measure of
Some of those measures. So you are not free to choose mu as you like. That's what the point I want to make. when you define something as the generalization of length, that something you are defining should enjoy properties of the length. One is like when it coincides with the intervals, the measure that you are defining should get me back the original notion of length. One thing. Secondly, length has this property. The sum of the whole is equal to, sorry, the whole measurement is equal to sum of its part. That I want to be there for mu as well. So mu of A1 union A2, I want to be coincide with mu of A1 plus mu of A2 whenever A1 and A2 are disjoint. Are you with me? So like this, you concentrate more and more on the length and see what are all the properties that are there in length that will guide us how to define this mu. And therefore, our hands are not as free as you think. Initially, I told you can define mu in any way. I want 2 power r to r some function. If you want just a function, you can always define, but that function you want to be generalization of the length. And for that, it should satisfy certain properties that length function has. Okay. One, length of open interval should be equal to the difference of the endpoints. And secondly, length of the whole should be equal to sum of its length and so on. Therefore, because of the same reason, if mu is defined like this somewhere here and mu is defined like this somewhere there, let us say A and B, then sometime you may not have freedom to define mu somewhere else. The already defined mu here and here will automatically tell you that mu should be defined like this in a particular set. You don't have freedom. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
You don't
Yes.
have freedom to define mu anywhere, everywhere like you can. Already defined mu on some subset will automatically will tell you that mu should be like this in another new set. That will automatically be determined. So you should be careful. You cannot define mu like this. And because, for instance, suppose I am dealing with, let us say 1, 2, union 3, 4. This is my set. Okay. 1, 2 alone, you know, length is 1, and 3, 4 alone, length, you know, it is 1. And if you want a natural generalization of the length for 1, 2 union 3, 4, what do you expect the measure to be? If I want mu of this, and if I want mu to be generalization of length, this should be equal to
2.
2. So you don't have choice. You don't have choice to define mu of 1, 2 union 3, 4 once you have already defined mu on 1, 2 and mu on 3, 4. Like this, there may be certain constraints that is naturally imposed by general principles of length. Okay, because of the same reason, what I have started with, that is 2 power r may not work. The mu should be defined like this in place x, mu should be defined like this in place y, will tell you that consistent with these two, I may not be able to define mu in a place z. I may not be able to define. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
So I cannot be ambitious and make my domain to be
Power set of
power set of R. I may not be able to define for any subset of R, but I may have to handle collection of suitable subsets of R. Okay, so let me write. Due to some constraints guided by principles of length, we may not be able to define mu for every subset of R. Mu at some place X is like this. Mu at some place Y is like this. Will tell you mu at some place Z should be like this. And it may also tell you that mu at some place cannot be defined at all, consistent with all these things. Okay. May not be able to define mu for every subset of R. Hence, we may have to be satisfied. We may have to deal with not 2 power R, but a suitable collection of subsets of R. Suitable collection of subsets of R. What is that suitability? That is again a question, but naive understanding is like you cannot have 2 power R. So your collection should not be as rich as power set, but at the same time, the collection should be rich enough to. Can you complete my statement?
Rich enough to
Contain all intervals.
intervals.
Contain all intervals, because I want to extend the notion of length. So I want to define length for any subset, some subsets of R. So when I want to take that subset as intervals, it should coincide with our usual length. Therefore, the subsets that I am taking should also include the intervals. So it cannot be rich enough to cover 2 power R. At the same time, it should be rich enough to cover all open intervals. Okay. Further, see, as I told you, once I have the measure for parts, I want the measure for its whole obtained by combining this. Okay. Therefore, this collection of subsets should have certain property. If I am defining mu on a collection of subset, that collection of subset have certain property. If A is there in the collection and B is in the collection, I can talk about measure of A, I can talk about measure of B, but I want to talk about measure of
A union B.
A union B. For that, I have to guarantee that A union B is in
In the collection.
in that collection. If it is 2 power R, I am guaranteed. But now I am not working with 2 power R. I am working with a suitable collection of subsets. So if that collection of subset includes A, it includes B, it should definitely include their union. Otherwise, I cannot target my guiding principle like the measure of the whole should be is equal to sum of the measure of its part. I cannot do that. Okay, so whenever you take the suitable collection, this suitability is determined by several factors. For instance, it should include union whenever it includes individual sets. Are you with me? And that leads to the concept of so-called sigma algebra. I will not define what is sigma algebra now. So in order to define measure, we will not take power set of R, we will take a suitable sigma algebra, namely suitable collection of subsets of R. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
And once I have defined that sigma algebra, what is the suitable sigma algebra I have to work, and then it will lead to what is we want as measure. So I will define mu from not 2 power R, but from a suitable sigma algebra on R and to R, and that mu should be consistent with the length for open interval, and it should satisfy certain properties that length enjoys, and that leads to the concept of measure. Okay, so message is that the moral of the story is that we want to measure subsets of R. Already there is a measure, for instance, length. But length is defined or makes sense only for intervals and intervals like sets. We want to have length for more arbitrary subsets. And for that, we want to generalize the concept of length, and that is what the concept of measure is. But when you try to generalize and make the concept of measure, what the guiding principle is, the property satisfied by the length. And that will tell you that there are certain conditions that this measure should satisfy. And that will also tell you that we may not be able to define measure for any and every subset of R. We may have to work on some special class of subsets, and that special class of subsets should have certain property, and that leads to the concept of sigma algebra. Okay, so is it clear? So everything naturally pop up. The definition of sigma algebra is to handle what type of subset I should take. The measure is to handle the generalized version of length and so on. Is it clear? I am going to stop with
Yes, sir.
this.
Yes,
Yes,
sir.
sir.
The
Yes.
question again
Yes, sir.
remains, why we are not happy with length and just intervals? Why do you want to extend it and try to define length for sets other than intervals? Okay, that's the question that we will answer in the next class. Again, first intuitively, before defining all these technical terms. So the question is, why we want to define or we want to generalize the notion of length. And define something called measure. Why do you want to do that? Okay, why can't you live just with intervals and their length? There comes the integration theory. Okay, so in the process of answering this, why you are not happy just with intervals and length, why do you want to extend length to other sets, at least some nice sets other than intervals? In the process of answering this question, the role of integration will come. Riemann integration, Lebesgue integration, and so on. So first I will explain intuitively why we want to generalize this using the concept of integration, and then we will start technically dealing with sigma algebra, measure, integration, and so on. Okay, it is the right time to stop.
Sir. Thank you, sir.
Okay.
Thank you, sir.
Any questions? So what is takeaway message from today is that measure and integrations are related. How they are related is yet to answer. Earlier measurements like length, area, and volume can cover only some special classes of subsets of R, subsets of R2, and subsets of R3. We want to generalize this. This generalized notion of length, area, volume, etc. are what is called as Lebesgue measure. Lebesgue measure in R will be generalized version of length. Lebesgue measure in R2 will be generalized version of area. Lebesgue measure in R3 will be generalized version of volume, and so on. In fact, you can work with any Rn. And in doing this generalization, naturally the idea of sigma algebra pops up. And further, the question that why do you want to generalize is yet to answer, but keep in mind that there we have to interrelate measure with the integration. Okay, to answer why do you want something other than length and open intervals, we want to seek help from integration, and we want to relate integration with the measure. Okay, with that, I stop. So I will stop recording and leave the meeting. Thank you.
Thank you.
Thank you, sir.